Hello. In this part of the lesson, I'm going to be talking about functions. As you continue through your math career, you'll learn that functions is one of the most important topics in mathematics. I'm going to begin by defining something called relations, domain, and range. Then I'm going to go ahead and define a function, and I'm going to finish up by illustrating something called function notation. So let's begin with some definitions. A relation is a set of ordered pairs. The set composed of all of the first coordinates of the ordered pairs is called the domain of the relation. And the set composed of all of the second coordinates of the ordered pairs is called the range of the relation. Now there's lots of different ways we can represent a set of ordered pairs. One way we can do it is with a table. So in this table, I am illustrating the relation that compares a student's age to a student's height. Notice that there are several ordered pairs in here, and I have several students that are aged 18, and they all have different heights. In this table, I'm illustrating the relation comparing the student's ID number to the student's height. Now, since each student has their own personal ID, in this table, I will not have one ID corresponding to two different heights. That's an important distinction between this table and the table we looked at comparing the student's age to the student's height, and we'll come back to that later in the lesson. Here, our relation, we have just explicitly stated the ordered pairs, and the question we're being asked is, what are the domain and range of the relation? Well, the domain is the set of numbers that make up the first coordinates in the ordered pairs. So the domain is the set 4, 3, 7, and negative 3.8. The range is the set of numbers that are the second coordinates in the ordered pairs. So the range is the set of numbers 56, negative 2.6, 9, and 4. Yet another way we can illustrate a set of ordered pairs is with a graph. Let's state the domain and range of this relation. I've gone ahead and sort of made this a fill-in-the-blank type question, and so let's look at our points kind of in a left to right order. The leftmost point is the point negative 4, negative 6. So one number that's in our domain is negative 4, and one number that's in our range is negative 6. The next point is negative 2, 5. So we can add negative 2 to our domain, and we can add 5 to our range. Moving on, we have the point 0, negative 3. 0's in the domain, negative 3 is in the range. We also have the point 3, 4. So 3's in the domain, 4's in the range. And finally, we have the point 4, 4. That first coordinate of 4 needs to be added to our domain. We don't need to add 4 to our range because 4 is already in our range. And once a number's in the set, it's there. It can't be there twice. A number can only be in a set or not be in a set. 4 is in the set. Here we have a verbal description of our relation. We have the set of points x, y, and the verbal part of the description is that y equals 2x and x is a natural number. Well, let's recall that the natural numbers are the counting numbers, 1, 2, 3, 4, etc. What happens when we take the counting numbers and multiply each of them by 2? We get the set 2, 4, 6, 8, etc. We get the even counting numbers. So in this example, the domain is the natural numbers, which are also called the counting numbers, so that would be a fine way of describing the domain. And the range is the set of even natural numbers. Now here we have a really new way of describing a relation. In this picture, we have arrows pointing from the numbers on the left to the numbers on the right. What's trying to be illustrated by this? Well, the implication is that the numbers on the left are the numbers that make up the domain, and the numbers on the right are the numbers that make up the range. And the arrows pair first coordinates with second coordinates in the ordered pairs that make up the relation. So let's go ahead and state the points in the relation implied by the diagram. So the relation is, well, one of our ordered pairs is mapping, that's a word that we use in this type of diagram, 7 to 6. So one of our ordered pairs is 7, 6. Another one of our ordered pairs needs to illustrate that 10 is mapped to 0. That would be 10, 0. Negative 4 is mapped to two different numbers. So we're going to have two different points in our set that have a first coordinate of negative 4. That's negative 4, 12, and negative 4, negative 4. Notice that negative 4 was mapped to two different numbers. That's something you want to keep in mind as I move on to the next example. In the next example, I have 4 numbers in the domain and I have 3 numbers in the range. We frequently talk about the numbers in the domain as being the input of the relation and the numbers in the range as being the output of the relation. So let's go ahead and write the points implied by this diagram. This time, the relation is the set of points. 6 is mapped to 7, 0 is mapped to 10, 12 is mapped to negative 4, and negative 4 is mapped to negative 4. In this relation, every input from the domain was mapped to only one output from the range. This type of relation is called a function. In the last diagram, negative 4 was mapped to two different outputs from the range. That relation was not a function. Let's go ahead and formally define what I mean by this word function. A function is a set of ordered pairs with the property that no two distinct points in the set have the same first coordinate. Well, let's think about this table. One thing we might ask ourselves is this relation also a function? Well, ask yourself this question. What if somebody asked you, how tall is the 18-year-old student? Well, there's not only one answer to that question. This 18-year-old student is 62 inches tall. This 18-year-old student is 65 inches tall, and this 18-year-old student is 67 inches tall. One input, 18 years old, is generating multiple outputs. Functions don't work that way. Functions have the property that one input generates exactly one output. On the other hand, if somebody asked you, how tall is student with ID number 97648, there is only one correct response to that question. Student with ID number 97648 is 65 inches tall. Each student ID number that you input will generate exactly one output. So this relation is a function. How about the set of ordered pairs that are graphically illustrated here? Is this relation a function? Well, what we have to ask ourselves is there any pair of points that have the same first coordinate? The reason we have to ask that question is because the defining property of a function is that no 2 points in the set have the same first coordinate. Well, we can see as we look at our graph that there's 2 different points that have a first coordinate of 4. This point has an x coordinate of 4, and since x is our horizontal axis, the first coordinate is 4 of this point. And this point here also has an x coordinate of 4. Since 2 distinct points in the set have a first coordinate of 4, this relation is not a function. How about this relation? The set of points x, y with the property that the sum of x and y equals 6. Is this relation a function? Well, what we have to ask ourselves is, if we input a number for x, are we ever going to get more than one number back for y? Well, that's a pretty easy question. We could take our equation, x plus y equals 6, and we could solve that for y. Y is equal to 6 minus x. When we write the equation in that form, it's pretty clear that if we input one single value for x, we're only going to get one single value back for y. So this relation is a function. Now, if we were to graph the equation y equals 6 minus x, we would get a line. And consequently, we call this type of function a linear function. And it turns out that almost any line you draw represents a function. As a matter of fact, there is only one type of linear relation that is not a function. What type of linear relation is not a function? So let's use this grid to help us think through this question. What makes a relation not a function? It's when 2 points have the same first coordinate. So let's just pick a first coordinate of, say, -2, and let's go ahead and plot 2 points that have a first coordinate of -2. Well, 2 points determine a unique line, and when we connect these 2 points, what sort of line do we get? We get a vertical line. And it turns out that anytime you connect 2 points with the same first coordinate, you get a vertical line. So the type of linear relation that is not a function is a vertical line. Vertical lines have other purposes when you're talking about functions. The set of points that lie on any curve is a function if and only if no vertical line intersects the curve in more than one point. So here we're being asked, is the set of points that lie on this curve a function? Well, let's start thinking about running vertical lines onto this graph. Here's a vertical line that's not intersecting the curve at all. Well, all right. Here's a vertical line that's intersecting the curve in exactly one point. Oh, no problem. Here's a vertical line that's intersecting the curve in 2 points. The vertical line test says that a curve represents a function if and only if no vertical line intersects the curve in 2 points. Here's a vertical line intersecting the curve in 2 points, so this must not be a function. What's going haywire in function land in terms of this curve? Well, this vertical line is showing us that the set of points on the curve includes both the points 4, 4, and 4, -2. And a function is a set of ordered pairs with the property that no 2 distinct points in the set have the same first coordinate. Consequently, the points on this curve do not constitute a function. How about the set of points that lie on this curve? Well, again, let's get out our handy-dandy vertical line, and let's pass this vertical line across the graph. And let's see if the vertical line ever intersects the curve in more than one point. And I think you can probably see a little faster than this line is moving, that no vertical line is going to intersect this curve in more than one point. Consequently, there are no 2 points on this curve that have the same first coordinate. Consequently, the set of points on this curve is a function. Here's a multiple choice question. Suppose that the domain of a function is the set of numbers 4, 5, and 6. Which of the following must be true about the range of the function? A, the range contains exactly 3 elements. B, the range contains at most 3 elements. C, the range contains at least 3 elements. You know those little mapping diagrams we looked at earlier? I think that'll help us think through this problem. So here's our domain on the left, and it has the numbers 4, 5, and 6. Well, if 4 is in the domain, there has to be some number in the range that 4 is mapped to. I'm just going to make a number up, 11. Well, the defining property of a function is that no number in the domain is mapped to 2 or more numbers in the range. But there's nothing that says that different numbers in the domain can't be mapped to the same number in the range. So it could be that 5 is also mapped to 11, and 6 is also mapped to 11. Our ordered pairs are 4, 11, 5, 11, and 6, 11. So it's possible that there's only one number in the range. How about if 4 is mapped to, say, 26? Well, it could be the case that 5 is also mapped to 26, but 6 is mapped to an entirely different number, like 39. So it's also possible that there's 2 numbers in the range. Of course, it could be the case that 4 is mapped to 12, 5 is mapped to 76. Again, remember, I'm just making these numbers up on the right. And 6 is mapped to negative 102. It could be the case that the 3 numbers in the domain are each mapped to different numbers in the range. So there could be 3 numbers in the range. So here's the question. Could there be a 4th number in the range? Well, in order for there to be a 4th number in the range, we'd have to have an arrow coming from one of the 3 numbers in the domain. But if we had an arrow coming from one of the 3 numbers in the domain to 67, we'd have two arrows coming from one number in the domain. In this case, 6 is being mapped to 2 different values in the range, which would mean my set would have 2 different points with a first coordinate of 6, and the set would no longer be a function. So the answer to this question is the range must have no more than 3 elements. Let's turn the picture around. Let's suppose that 4, 5, and 6 were the numbers in the range. What do we know about the domain? Does it contain exactly 3 elements? Does it contain at most 3 elements? Or does it contain at least 3 elements? Well, we need to have some number in our domain that gets mapped to 4. So let's say 7. So I have the point 7, 4 in my set. We also need to have some number that maps to 5, and it can't be 7 because I can't have 2 different points with a first coordinate of 7. So I'm going to add another number, say 19, and let's say that's what's mapped to 5. We need yet a 3rd number in our domain because we need something to map to 6, and it can't be 7 or 19. So let's put 22 into our domain and map that to 6. So our domain needs to have at least 3 elements. Could it have a 4th element? Sure it could, because there's nothing in function land that says we can't have 2 inputs generating the same output. So I'm going to go ahead and add 5 to my domain, and we can see that the answer to the question here is that the domain must have at least 3 elements. Okay, let's move on to function notation. All right, let's find the point on the function that has an x-coordinate of 4. Well, if x equals 4, then since we're working with the set of points where y equals x squared minus 2x, y must equal 4 squared minus 2 times 4. 16 minus 8 is 8. So the point in this function where x equals 4 is 4, 8. Now that's a whole lot of writing to answer a pretty simple question. Wouldn't it be nice if we had some more compact way of answering this question completely? Well, lucky for us, a committee a long time ago got together and came up with something called function notation that makes us have a nice, easy, abbreviated way of communicating all of the information I just communicated with these words. We frequently talk about y being a function of x. X is our horizontal axis, y is our vertical axis, and we get our inputs off the horizontal axis, and our outputs are the y-coordinate of the corresponding point on the function. So in this example, the y-coordinate is generated by the formula x squared minus 2x. And we input a value for x. Our function works its magic, and it outputs a value for y. So suppose that we input 4 for x. Well, when the function applies the formula x squared minus 2x, it outputs 8, and that's the value for y. So when we input 4 for x, the output for y is 8. Let's give this function a name. Let's name the function f. We're now have set the stage for what we call function notation. I'm going to take the y in the equation y equals x squared minus 2x, and I'm going to replace it with the symbols f of x. Now, when this symbol came up, you may have thought I was going to say f times x. And that's a natural thought because to this point in Math 60 and 65, every time we've had an expression inside parentheses, we've thought of those parentheses as serving as grouping symbols that would indicate multiplication if some other symbol occurred before the parentheses. Here, the parentheses are serving a completely different purpose. Let me say that again. Here, the parentheses are serving a completely different purpose. This set of symbols is read f of x. And what it's saying is, when we input a value for x, the output from the function f is determined by the formula x squared minus 2x. Now, I have a suggestion for you. Since you're not in the classroom, you're probably not going to be talking about this language as much as a student would in the classroom. So I suggest you pause the tape and you literally say 5 or 10 times, f of x equals x squared minus 2x, so you can start getting used to thinking of these parentheses being used in this new and novel way. Alrighty, so when we input 4 for x, the output was 8 for y. So what we say here is that f of 4 equals 8. Say that out loud. F of 4 equals 8. Each input from the function's domain generates exactly one output from the function's range. The number output by the function is called the function value. So when we read these symbols, f of 4 equals 8, we're basically making shorthand statement that 8 is the function value of f when x equals 4. The function value of f when x equals 4 is the number 8. The letter f is almost exclusively reserved for function names. This helps minimize confusion between function notation and multiplication. You'll almost never see the letter f used as a variable because we want you to know that when you see f followed by parentheses, it's almost certain that we're talking about function notation, not multiplication. G and H are also frequently used as function names. Let's see some examples of using function notation. Again, we're going to stick with our example where y equals x squared minus 2x, except now instead of identifying the output as the letter y, we're identifying the output with the symbols f of x. I've gone ahead and put parentheses around both occurrences of x in the formula because I think it will help you visualize what's going on when we apply function notation. What we're going to have to do is take whatever number we're replacing for x. In our first example, that's going to be 4. And we're going to have to replace x with 4 in all 3 occurrences of x in the equation. So I need to take that 4, and I need to substitute it for x on both the left side of the equation and both occurrences on the right side of the equation. So let's go ahead and do that. F of 4 is equal to, well, when I have x in parentheses squared, that's just saying square the number inside the parentheses. The number inside the parentheses is 4, so I need to square 4, and then I need to subtract 2 times the number in the parentheses, 2 times 4. And we already saw that this equals 8. Notice that that tells us that the set called f includes the point 4, 8. Also, if we were looking at a graph of this function, one of the points on the curve would be the point 4, 8. Let's evaluate f of 7. Everywhere I see an x in my formula, I need to write down 7. But notice that in the second occurrence of 7, 7 squared, I don't really need those parentheses. So if I was really working this problem on my paper, what I would write is f of 7 equals 7 squared minus 2 times 7. Let's see, that's 49 minus 14, which is 35. What does this tell us? Well, one of the things it tells us is that the set f includes the point 7, 35. How about f of negative 3? Everywhere I see an x in my formula, I need to write down negative 3. This time, even when I'm working this on my paper, I'm going to need all of those parentheses, because the only way I can correctly communicate that I need to square the number negative 3 is if the number negative 3 is in parentheses. So this time I am literally going to write down f of negative 3 equals negative 3 in parentheses squared minus 2 times negative 3 in parentheses. So this time I have 9 plus 6, which is 15. So this tells us that the set, if we were looking at a graph or a table or whatever form we were looking at the function, it would include the point negative 3, 15. Let's find these 3 function values for the formula f of x equals 2x plus 7. It might help you to go ahead and write down an expression of this formula where x is in parentheses, just to help you visualize that wherever you write, whatever number you write in the parentheses on the left, you need to write the same number in the parentheses on the right. So f of 4 is going to be 2 times 4 plus 7, which is 15. F of 0 is going to equal 2 times 0 plus 7, which is 7. And f of negative 6 is equal to 2 times negative 6 plus 7, which is negative 5. How about f of negative 2 and f of 10 when f of x equals 2x squared minus x plus 57? This might be a good place for you to pause the tape and see if you can figure this out before you watch me work it. It might help you if you went ahead and rewrote this formula with x in parentheses on both sides of the equal sign. I would just do this the first few problems that you work to help you see that you're literally just replacing all 3 occurrences of x with whatever number is in the parentheses. So f at negative 2 is going to be 2 times the square of negative 2 minus negative 2 plus 57. Well, that's 2 times 4, which is 8, plus 2, plus 57, which is 67. And f at 10 is 2 times 10 squared minus 10 plus 57. Notice I didn't put parentheses around 10 when I was subtracting it because you don't need parentheses around 10 when it's being subtracted. So this is 2 times 100, which is 200, plus 47, which is 247. Now you may have noticed that on this screen I said f at -2 and f at 10. You'll frequently hear people use that language. F at 10, f of 10 means the same thing. How about finding f of 6, f of 4, and f of 3 when f of x equals 27? This type of function throws most people for a loop the first time they encounter it because they see x on the left, but they don't see x on the right. And so they don't know what to do with the 6, what to do with the 4, what to do with the 3. Well, I'm going to give you a little crutch to help you get used to this type of function. We can think of f of x equals 27 as f of x equals 0 times x plus 27. Notice here that the parentheses on the right are indicating multiplication because you can't have a function named 0. On the left, the parentheses are part of function notation. On the right, the parentheses are used to indicate multiplication. And you know what? It doesn't matter what number we multiply by 0. The result is 0, and when you add 27 to 0, you get 27. So this is a legitimate representation of our function f of x. Now, when we replace x with 6, we have a place to write it on both sides of the equal sign. F of 6 is 0 times 6 plus 27. 0 times 6 is 0. When you add 27 to 0, you get 27. F of 4 is 0 times 4 plus 27. When you do this arithmetic, what do you get? 27. F of 3, 0 times 3 is 0 plus 27. Guess what? We got 27. It doesn't matter what we replace x with. The end result is 27. So I think that I can go ahead and put in a couple more numbers. What if I input 400? Well, I can see my pattern. I'm going to get 27. What if I input -1/2? Well, I can see my pattern. The output's going to be 27. This type of function is called a constant function because the output is constant. No matter what number we input, the output is 27. One last example. Let's find f of 6, f of -19, and f of t when f of x equals 8 minus x. Well, f of 6, our formula tells us basically that we need to subtract the value of x from 8. So f of 6 is going to be the result of subtracting 6 from 8. And that result is 2. How about f of -19? Well, we need to subtract -19 from 8. And that's going to result in 27. When we found f of 6, we subtracted 6 from 8. When we found f of -19, we subtracted -19 from 8. So I guess when we find f of t, what we need to do is subtract t from 8. T and x are sometimes called dummy variables. And as long as you use the same dummy variable on both sides of the equal sign, it doesn't matter what letter you use to represent the input of your function, because once you replace that letter with a number, you're going to get the same result. And that is the end of Lesson 18.
1, 2, 3.